The reason why I'm going so slow is the more you understand the basic foundations of SN2 and E2, everything else is going to pop into place. All right. And these four reactions make up a good chunk of probably of your next test, right? I don't know what else you guys are going to cover, but it's really important to understand the basic principles, because now you are going to take all of this information and it's going to keep popping up in the rest of organic chemistry when you think about why do things react the way they do. Which I know you all just really want to hear right now. This is totally making your night. I can see Melissa and Matthew and Max just all smiled, and I'm assuming that that's just because that's pure unbridled, passion and joy. But going back to our question.
I have a quick question.
Yes.
So this was actually from like when we were still covering like SN2. So you know how like it flipped like the carbon, like the direction that it was pointing. That doesn't happen in SN1 reactions because like first you just pop off like the bromine and then you attach the hydroxide.
Yeah. So how about we finish SN2 and then I will tell you why that is. But there's a very simple reason. But Max, how's it going?
Pretty good.
Okay. Just making sure you guys are all still with it. So you all look so happy today, and I really don't want to ruin that buzz for all of you. I would hate to be the person that does that, because you guys seem really happy. Yeah, I'm also really happy because tomorrow is match day for doctors. Doctors find out where they get their residency or internships, stuff like that. And my last class full of doctors are finding out because they're graduating. Kids that I taught back at Purdue are graduating from med school. They're finding out where they're going. And I know a lot of them that go to IU, Indiana University School of Medicine, and they shared the link with me, so I get to watch tomorrow in real time. And I'm going to watch and see where they go, like where they get to do their residencies and stuff. So I'm super excited. I've never been able to see this, so I'm going to have popcorn and a Coke and just watch on my TV. But enough about that. So we came back to this.
Chicken nuggets?
Maybe chicken nuggets. You know me too well. So coming back to we had our SN2 reaction, right? We had our hydroxide coming in, and we had our methyl bromide ready to react. Oh, sorry, these are H's, not methyls. Yep. Like that. And the question I asked you was, which solvent would be better, acetone or water? And remember, we want our reactions to be able to go forward. Our solvent should help that. So which one did you guys choose? Acetone A or water B?
I chose water.
Okay.
I said acetone.
I am conflicted.
So Melissa, you are our deciding vote.
See, it's just I have reasons for both. Because in a way,
aren't they all winners?
Huh?
I said, in a way, aren't they all winners?
Well, yeah, because I don't know. In a way, I think that like the acetone could like help speed up the reaction. That just makes sense in my head. But then in my head, I'm like, wouldn't I don't know, because I remember biology, and I'm like, oh yeah, H plus, like that's a good thing. So I don't know why I'm just thinking of that.
So, which one you have to pick one? You've got to choose one, A or B.
I'm gonna go with acetone.
Okay, so we have 2 votes for acetone and 1 vote for water. So our hydroxide is our nucleophile, right? It's a good nucleophile. Can hydroxide react in any other way? Do we normally think of hydroxide as any other type of reactant that you guys have used before in lab? Starts with B.
Bromine.
Nope, base.
Oh, wait.
Right? Sodium hydroxide is a base, right?
Yeah.
So if I put water in there, this can act as a nucleophile, and it can act as a base and remove that proton. Which one is it going to prefer to do? Acid-base. Acid-base chemistry is your quickest chemistry besides radical chemistry. If I put a solvent in there that's polar, protic, I am going to slow the rate of my reaction down. Reaction rate will decrease. Bad. Because I have now introduced competing chemistry. When I want my reactions to go through, I want less competition, right? It's like if I apply for a job, it's easier if no one else is applying, right? But if you start bringing in other people, then you've got to compete against them and hopefully be better. I mean, this is an issue that you normal people have to deal with. Not me, I'm great. So I always win. But this is the idea here, is that if I introduce a solvent, though, like my acetone does not have any type of protic proton, right? But if you guys remember your chemistry of dipole moments, acetone is polar, so it has a partial negative side and a partial positive side, and now this partial positive side can help keep that OH minus relatively stable, right? It keeps it relatively stable because minimizing charges are good, but it's just a minor stabilization. It's not enough to impede the reaction. So this is really, really good to have. This is why polar solvents are good for SN2. They help stabilize, and also when you're going through your intermediates, they help stabilize stuff. Your polar solvents also are going to come into play when we start talking about SN1 reactions, but this is good. So now, when you have SN2 reactions, you are always going to prefer polar aprotic. Just because if you have a good nucleophile, it could be a good base. And if you have that, you're going to introduce competing chemistry. And that's always, always troubling. So the next question I know you guys are going to be asking me, because I can see it forming in Mag's head. Well, how will I know if it's a polar protic solvent? Do you have any idea how to tell? Can I erase this or are you good?
Does that have to do with something about the amount of hydrogens on the atom in that molecule?
Yep, but there's something even easier. If you see an OH somewhere on your solvent or an NH, doesn't matter what. If you have a hydrogen attached to an oxygen or a hydrogen attached to a nitrogen, that is going to be a polar protic solvent. This is the easiest way to tell if it's polar protic. Now, if you're like me and someone who just says, well, what about, just to make sure, here are some of your more common polar aprotic solvents. So common polar aprotic solvents. Acetone, DMSO, sorry, as I'm thinking about my other, acetone, DMSO, DMF is a good one. Oh, can't spell DMF. And then acetonitrile is good. I think. So I'm going to draw them out, and then you can tell me or not whether or not it meets that of not having that condition. So this is acetone. This is DMSO. This is acetonitrile. And this is DMF. So do you see any nitrogen to hydrogen bonds or oxygen to hydrogen bonds here? Yep, and this is why these are your common polar aprotic solvents. So now, this is how you start putting it together. You want to treat this as a puzzle, meaning when you look at these reactions, and the hardest part of this part of the class is identifying what reaction is going to happen. Is it SN2? Is it SN1? Is it E1? It's E2. Now you all know what's the first thing you should look at.
The nucleophile?
Not the nucleophile. SP3, first make sure that it is capable of this, right? But then you check the substitution. Because remember, if you have a tertiary carbon, can you have an SN2? Nope. So if you have a methyl, has to be SN2, right? And we'll go through and talk about each of these, but this is the idea of starting to rank them and say, I look at my substitution that limits me and tells me what it's going to be. I look at my, is it a strong, if I'm unsure, I look at if it's a strong or weak nucleophile, such and such. So before we jump to the other reactions and before I answer Melissa's question about the R or S conundrum that we had with the SN1, I'm going to give you a chart that is going to be your lifeblood and you must commit this to memory. I know I say that a lot, but this one I do mean. I will yell at all of you if you don't commit this to memory. I'm just kidding. I'll just yell at Melissa. I won't actually yell at Melissa. I would feel bad if I yelled it. I'd feel bad if I yelled at anyone on this call right now.
I would cry, actually.
That's why I wouldn't yell at you, because I know I would make you guys cry. Mags, maybe not. Mags might beat me up. That might be why I don't want to make her mad. Maybe she might cry and then beat me up. I don't want to take that risk. So this is a very important chart because we're going to figure out whether or not these reactions can occur based on the substitution of the carbon, right? And remember, it's just how many other carbons are attached. So for SN2, let's double check. Can I do an SN2 on a methyl carbon?
Yes.
Yes, you can. You can also do an SN2 on a primary and a secondary, but you cannot do it on a tertiary. Okay. So, as I've said before, SN1 and SN2 are similar, right? The only difference is what's happening. But all that's going to happen now is that we're simply going to flip it. A tertiary can happen for an SN1 and a secondary can happen for SN2, but you cannot have a primary or a methyl. And when I answer Melissa's question, it's going to show us why. Okay. So now if I was to ask Melissa, actually I'll ask Max, because Max was here at the beginning. Remember I said that SN1 and SN2 are similar, E1 and E2 are similar, but SN1 and E1 are similar, SN2 and E2 are similar, right? So knowing what you know about SN1, what type of carbons do you think E1 reactions can involve? I see your thinking face. It's a good thinking face.
The secondary and tertiary.
Correct. You cannot do an E1 with a methyl or primary. And now, Melissa, knowing what you know, can you tell me which carbons can undergo an E2?
The methyl, primary, and secondary.
Primary, yes. Secondary, yes. Tertiary, yes. Actually, methyl, no.
Oh.
So what did you just notice about our methyls now?
It can only occur with SN2 reactions.
Yes. If you ever get a question with a methyl halide, like a methyl halogen, like a bromomethyl or chloromethyl, it has to be SN2. Cannot be anything else. When we get into the E reactions, we'll talk about why that is, and it's like, it makes sense. But this is a very important chart because when you think about what type of chemistry is happening, when you are trying to predict, you should be able to take a look here, right? So the type of carbon is going to be your first thing. The next thing is going to be, do I have a strong nucleophile? Do I have a strong base? Do I have a weak nucleophile? Do I have a weak base? But we'll get more into that when we get to the elimination reactions. And so if you look at the primary, only SN2 and E2 can occur. If you look at tertiary, SN2 can't happen. So which type of carbon do you think is going to pop up the most in your problems?
Secondary.
Secondary, because every type of reaction can occur. But this is why you go through your checklist. So the first thing you do is see what type of carbon it is. That will help limit it, hopefully. If it's a secondary, well, then you just go on to the next thing. You check to see, do I have a strong nucleophile or a weak nucleophile? All right. After you get past that hurdle, then you can look at the solvents. Does that make sense?
Yes.
Okay. So now, can I erase this so you guys are good on this?
I'm good.
I'm good.
Okay. So now we're going to go back and answer Melissa's question, because now we're going to introduce the idea of SN1. So it's still nucleophilic substitution. However, this is now unimolecular, meaning only one thing is involved at a time. So in SN2, we used a strong nucleophile. So what type of nucleophile do you think we're going to use here?
Weak one.
Yep. So now instead of OH minus, we are going to use water. And instead of a primary or a methyl, which is preferred, we are going to use a tertiary. And so in our last reaction, right, I'm going to draw this. It was bimolecular because my nucleophile attacked my electrophile, right? So my leaving group left at the same time. It was both molecules were involved. But in an SN1, one thing only occurs at a time. So what should be the first thing that occurs in an SN1 reaction?
Leaving group.
The leaving group does what?
I mean, it's gone.
Leaves. So the arrow for this is just the bond onto your leaving group like that. And that's always just how you do that. And so if you see a tertiary, usually a good indicator. I think for tonight, we'll probably finish up with these, but I will host a video on Saturday. You guys don't have to come, but I will focus on elimination reactions. That way you have it handy on YouTube. And if you guys want to come, you can. I can also do it earlier in the day. I'm not set to be holding anything, so just let me know. So leaving group leaves, all right? And so what we end up getting now is that, do you remember when we had that intermediate, or not intermediate, we had that transition state?
Yes.
Remember, it was really weird. We get the same thing. Because now, what is interesting about our carbon? Since the bond goes on to the bromine, the bromine took those electrons with it. So what's true about my carbon now? It just lost 2 electrons. It is hypovalent. It is missing 2 electrons. It only has 6 valence electrons right now. Therefore, we form what is called a carbocation. So, carbocations, Matthew, stable or unstable?
They are unstable.
Extremely, because it is hypovalent. It is missing electrons. So, when we were talking about what type of carbons will undergo SN2 or SN1 reactions, right? We said tertiary and secondary. So Mags, what do you think helps stabilize these carbocations?
Electrons?
Well, yeah, electrons stabilize them, but in the form of what type of bonds?
Pi bonds.
Nope. Carbon-carbon.
Oh.
So carbon-carbon bonds stabilize carbocations. So this is the first thing that stabilizes your carbocation. This is why a tertiary is more stable than a secondary is more stable than a primary is more stable than a methyl. Every carbon-carbon bond you have that is attached to your carbocation stabilizes it. It's still not great, but every one you add makes it more stable. So a tertiary carbocation you can form. A secondary, it can form, but it's not great. You cannot form a primary one, and methyl ones don't form. You have to go to extraordinary lengths for that to happen. The second thing, and this is something that just comes up every now and then. I don't know if you guys talked about hypervalent? Sorry, not hyper.
I think so.
Not hypervalent. Hold on, I'm trying to think. That's called. As this is what happened as you get older and you stop teaching this. So essentially what is going to stabilize it is going to be the more carbons you have attached, and then adjacent hydrogens are also going to stabilize it. So the hydrogens on these carbons are also stabilizing that. Have you talked about that effect?
I think so.
Yep. So basically, the idea here is that this is going to stabilize it. So the more hydrogens you have on adjacent carbons, hyperconjugation, this is what that's called. Sorry that left my mind. This is the fancy term. Have you mentioned hyperconjugation? If you haven't, I'm not going to go into too much detail. But if your professor ever asks you what two things stabilize, carbon-carbon bonds stabilize, carbocations, hyperconjugation. Resonance can stabilize it as well. So resonance can stabilize it. I think that's what you were meaning by our pi bonds, right, Max? Yep. So pi bonds or resonance can stabilize it. And I'm going to show you what we mean by that. But when you form this carbocation, right, this wonderful carbocation, let me know when I can erase so I can clear some space off. Good?
I'm good.
All right. So when I have my carbocation here, and I've lost my bond and my electrons, what is the hybridization of this carbon at this moment?
sp2.
Mm-hmm. It is sp2. All right. This is why Melissa's question is going to come into play now. So what orbital has not been put into the hybridization? What orbital is just hanging out and not doing anything?
D dash.
Nope, that's your methyl. You're not including your unused other p orbital, which is a pi orbital. And that p orbital, remember, kind of looks like a bowling pin. It's sticking out this way and it's sticking out that way, right? So basically, and I think it might be a little easier if you draw this way. So the idea here is that you just have this pi bond like that, right? And this is a carbocation, meaning we talked about how in SN2 we had a strong nucleophile. In SN1, we have really good electrophiles. Carbocations are really, really, really good electrophiles. They really need that electron density. So now that's why if I bring in any type of nucleophile, like water is a very terrible nucleophile because it's neutral. It has a full octet, but now my water can come in very easily and attach like that. But Melissa, is that the only way I can come in?
No.
I can come in from the other side because both sides of that p orbital are empty. Mm-hmm. So I can attack from either way. So now this is why when you have some type of stereocenter for an SN1 reaction, you are going to get 50% R and 50% S. Because you create this sp2 carbocation intermediate. And because it is a carbocation intermediate, any nucleophile can come in and it can come from the top or from the bottom. And so that's why you're going to get an even mix because there is no preference. Does that answer your question?
Yes.
I see maybe a little confusion from each of you. Your smiles are slowly fading and I'm slightly concerned.
For me, it makes sense, but I think I'm confusing what we were doing with something that we did in class on Wednesday. That was literally just like the same thing. Like you just like the leaving group leaves, and you have a like carbon cation, and then like whatever you're attacking and just replaces that.
Yep.
So I thought that was what we're doing, and that's why that happened. Because I thought like that maybe like, oh, if what we just did was SN2, that means that like this one was SN1. But now I'm not sure. But that's kind of like where my confusion comes from. But this makes sense.
Okay, so this is an SN1. Your leaving group leaves, you form a carbocation, then your nucleophile attacks, and it can attack from either way. Mags, what's up with you?
I think I get it.
Okay. Now it's the time for questions. Matthew, how you doing?
I think I'm understanding a lot more. Last week, I didn't know what she was talking about for like the entirety of everything.
That was me.
Okay. But this is basically all that happened. So I'm going to give you a practice problem, and I want you guys to just give me the answer. I'll give you a minute or so to work on it. So I think I'm going to order a pizza tonight and just stay up playing video games. I haven't done that in a while.
That is literally my plan for the night.
Say that again?
That is literally what I was planning on doing. I literally just ordered pizza like 10 minutes ago.
I ordered pizza too.
Nice. Mags, you have to. Mags, I'll order you a pizza if you need one.
I
just imagine she like lifts up a pizza. She's like, I'm eating one right now.
made mushroom soup, so I think that's what I'm gonna have for dinner.
That sounds good.
That's good.
I like mushrooms.
Mushrooms are good.
I watch cooking shows, and like when they use those fancy mushrooms, like cremini mushrooms and other stuff like that, I'm always jealous.
Yeah, you usually use the oyster mushrooms to make
Yeah.
vegetarian fried like chicken. That's what I like use them for.
Okay. Are you vegetarian?
Yeah.
Okay.
Yeah.
That's good. If you eat a lot of Mexican cuisine, I imagine Mexican cuisine vegetarian is probably really good.
Well, I don't know. I might stub when I go see my mom because she
I
makes
guess
really
that's
good
true.
food, and it usually has meat. So
That's fair. But I mean, like Mexican food, the tasty part, the cheese and the salsa and all that other stuff, right?
Yeah.
That's, unless you're vegan, that's very hard to replace. I know you can do it, but
vegans are I don't know. I can't imagine like not eating cheese and stuff.
okay. So you should get 2 answers for this.
Uh-oh.
You should get your original version, but now you are going to have the new nucleophile on there. And then like that. So you'll get 50% this. But now you are also going to get the other version. Like that. So now we just inverted that stereo center, right? So don't forget, whenever you have an SN1 reaction, you are always going to get 2 products if it's the stereo center.
And then the arrow would just push out the chlorine, right?
So, well, this is just the product. We'll go through and do the mechanism now. So for the product, right? Can I clear this?
Yes.
Okay, so for our mechanism, and I'm just going to draw a simpler version because I don't feel like drawing all of it. But in our first step, this pops up like this. So then you form your carbocation, right? And then our nucleophile in this case, which was water, will come like that. And you can draw it coming either way, it doesn't matter. Only if, I would say, just if your professor asks for the mechanism, oh, her pizza's there. If your professor asks you to draw the mechanism, only if she says draw both do you draw both. Just pick which one direction to go from. It doesn't matter which one you go for. And so then at the next step is that happening again? I hate, is that now you're going to have your water attached to it like this. All right. And so this is the one thing you have to watch out for. When you use a weak nucleophile that is protonated, such as water or an alcohol, you have to have an additional step. Do you guys know what that additional step's called? Deprotonation. Because you need to remove one of these extra protons. And so it doesn't matter what you can say, like water could come in here and do it like that. Or you could say a base like that, doesn't matter. And then you get your final product. Which is just an alcohol. So if you ever use water or an alcohol as your nucleophile in these reactions, you have to have that third step, which is deprotonation. How are you guys sitting on that one?
Makes sense.
Okay, how are you guys feeling about SN1 and SN2 distinctions between those?
Good.
Okay. Are you sure? Okay. So let us go through now. And are you still writing down?
I'm sorry.
Okay.
I'm good.
So now let us go through and highlight the differences, SN1, SN2. And I have something for you guys at the end of today's lesson that you will find very useful. So substitution, methyl, better than primary, better than secondary. SN1, tertiary, better than secondary. Nucleophile strength, strong, weak. Solvent, polar, aprotic. Get your pizza.
Yeah.
SN1 prefers polar protic. And the reason why it prefers polar protic is that since we are using weak nucleophiles, polar protic solvents are more polar. They can help stabilize those carbocations a lot better. Does that make sense? So here are the main differences between our substitution reactions. It's just one does this, and this is how you tell the difference. Really, the key indicator is whether or not it's the primary or methyl versus a secondary tertiary. And then if it's a secondary, then you look at the strength of the nucleophile and the solvent, and that'll usually key you in as to which one's the difference is. All right, so I'm going to send you guys something if you're done writing, because I feel that this is a good place to stop because we have differentiated between the substitution reactions. Actually, would you guys prefer to meet tomorrow or Saturday? I don't have, I mean, if you're just going to watch the video recording, that's fine, but.
Either work for me.
What if we did both days? Because I have a feeling you guys probably need a little more help to catch up on stuff since I missed last week with you guys.
Yeah.
Okay. What time tomorrow works?
Anytime after like 4 because I have my ASU appointment.
Ooh, someone's fancy. Sorry.
I have a meeting at 5:30 tomorrow.
Okay, so do you just want to do the same 6 o'clock time, and then whenever you're done, Matthew, if you can join, you'll join, and Melissa may or may not join?
Yeah.
Okay, but it'll be on YouTube, and I'll post this one when we're done. But I'm going to stop the video here, and then I'm going to open up a new meeting just for one last thing, because I'm going to email you guys something, and this is going to be very helpful for you. I promise you. So I will be back in just 1 second.